Finding LCM using the Prime Factorization Method. Hello everyone. Today we are going to dive into a very important topic in number theory, finding the least common multiple, or LCM, using the Prime Factorization Method. To start off, let's clarify what we actually mean when we talk about the LCM. If you have two or more positive integers, the least common multiple is simply the smallest positive integer that can be divided by each of those numbers without leaving any remainder. In other words, it is the smallest number that is a perfect multiple of every number in your set. Now, you might already know a few different ways to find the LCM, such as listing out multiples. However, as the numbers get larger and more complex, listing them out becomes quite tedious and prone to error. That is why we use the Prime Factorization Method. It is one of the most systematic and reliable approaches you can use, especially when you are dealing with much larger numbers. The beauty of this method lies in what we call the Fundamental Theorem of Arithmetic. This theorem tells us that any composite number can be broken down into its own unique set of prime components. By breaking our numbers down into these basic building blocks, we can use a very specific rule, which we will discuss in the next slide, to accurately construct the LCM. Let's move on to understand the core concept behind this process. The concept, the greatest power rule. One thing you must keep in mind is that finding the LCM is a different mental process than finding the highest common factor, or HCF. When we look for the HCF, we are searching for commonalities. We only care about what the numbers share. But for the LCM, we aren't just looking for what is common. Instead, think of the LCM as a container. For a number to be a multiple of all our original numbers, it must be large enough to contain every single prime factor present in every number we are working with. So, here is the formal definition to memorize. The prime LCM is the product of the greatest power of each prime factor that appears in the prime factorization of any of the given numbers. Now that we've introduced what the least common multiple actually is, let's look at the core logic behind this method. In simpler terms, once we break our numbers down into their prime components, we look at every prime number that shows up, and we pick the one with the largest exponent. We don't skip any primes, even if they only appear once. In the next slide, I will show you the exact step-by-step procedure to put this rule into practice. Step-by-step procedure. Now that we understand the core concept, that the LCM is all about capturing the greatest power of every prime factor involved, let's break this down into a clear step-by-step procedure you can follow every single time. First, we start with prime factorization. Your first task is to break down each of your given numbers into their prime components. Now, a quick tip from my side, I highly recommend writing these in exponential form. For example, instead of writing 2 times 2 times 2 times 3 times 3, write it as 2 cubed times 3 squared. This makes the next steps much easier to manage. Second, you need to identify all primes. Look through all the factorizations you just created and make a list of every single prime number that appears in any of them. And be careful here. Even if a prime number appears in only one of your numbers and not the others, you must include it in your list. We aren't just looking for common factors like we do with HCF, we want everything. Third, we select the highest power. For every prime number you listed in the previous step, scan through all your factorizations and pick out the one with the largest exponent, that is the greatest power. We want the strongest version of each prime. Finally, the last step is to calculate the product. Simply multiply all those highest powers you selected together. Once you find that final product, you have successfully found your LCM. In the next few slides, we are going to put this exact 4-step process into practice with some concrete examples to see how it works in action. Detailed examples. Now that we have understood the theory and the greatest power rule, let's put it into practice with our first concrete example. Let's look at example 1, which is a basic calculation. Our goal here is to find the least common multiple, or the LCM, of 12 and 18. We will follow the 4-step procedure we just discussed. First, step 1, prime factorization. we need to break both numbers down into their prime components. For 12, we have 2 times 2 times 3, which we can write in exponential form as 2 to the power of 2, multiplied by 3 to the first power. Now, for 18, we have 2 times 3, which we write as 2 to the first power, multiplied by 3 to the power of 2. Next, step 2, identify all primes. Looking at both our factorizations, we simply list every prime number that appears. In this case, the only prime factors involved in both numbers are 2 and 3. Now, moving to step 3, select the highest power. This is the most critical part of the method. We look at each prime individually. For the prime number 2, we have 2 to the power of 2 and 2 to the power of 1. We must choose the greatest power, which is 2 to the power of 2. Now, for the prime number 3, we compare 3 to the power of 1 and 3 to the power of 2. Again, we select the greatest power, which is 3 to the power of 2. Finally, step 4, calculate the product. To find our answer, we multiply these highest powers together. So, the LCM of 12 and 18 equals 2 squared times 3 squared. When we calculate that out, 2 squared is 4 and 3 squared is 9. 4 times 9 gives us 36. So, our final answer is 36. This means 36 is the smallest number that can be divided by both 12 and 18 without any remainder. In the next slide, we will see how we can apply this exact same logic to a real-world word problem. Detailed examples continued. Now that we have mastered the basic calculation with 12 and 18, let's see how we can apply this method to a real-world scenario. Imagine you are walking down a street and see 2 neon signs. Sign A is programmed to \text flash every 15 seconds, while sign B flashes every 20 seconds. If both signs flash at the exact same moment right now, we want to figure out how many seconds will pass before they next flash together. To solve this, we aren't just looking for a common number. We are looking for the smallest interval that both 15 and 20 can divide into perfectly. This means we need to find the least common multiple of 15 and 20. Let's follow the same 4-step procedure we used in our previous example. Step 1, prime factorization. We break both numbers down into their prime components. For 15, we have 3 to the power of 1 multiplied by 5 to the power of 1. For 20, we have 2 to the power of 2 multiplied by 5 to the power of 1. Step 2, identify all primes. Looking at both sets of factors, we need to list every prime number that appears. In this case, our list includes 2, 3, and 5. Remember, even if a prime only appears in one number, we must include it. Step 3, select the highest power. Now, we apply the greatest power rule we discussed earlier. For the prime 2, the highest power present is 2 squared, which comes from our factorization of 20. For the prime 3, the highest power is 3 to the power of 1 from 15. Finally, for the prime 5, the highest power is simply 5 to the power of 1, which is present in both. Step 4, calculate the product. We multiply these highest powers together. So, our LCM of 15 and 20 equals 2 squared times 3 to the power of 1 times 5 to the power of 1. When we calculate that out, it is 4 times 3 times 5, which gives us 60. Therefore, our conclusion is that the 2 neon signs will flash together again after 60 seconds. This same logic applies even if we increase the complexity, as we will see in our next example involving 3 different numbers. Detailed examples continued. Now that we have mastered finding the LCM for 2 numbers, let's increase the challenge slightly. In this third example, we will apply the exact same systematic process to find the LCM of 3 different numbers: 24, 36, and 40. First, let's move to step 1, prime factorization. We need to break each of these down into their prime components using exponents. For 24, we have 2 cubed times 3 to the power of 1. For 36, it breaks down into 2 squared times 3 squared. And finally, for 40, we have 2 cubed times 5 to the power of 1. Next, step 2, identify all primes. Looking across all 3 factorizations, we need to list every unique prime number that appears. Even if a prime only shows up once, we must include it. Here, our list of primes is 2, 3, and 5. Now, step 3, select the highest power. This is the most critical part of the greatest power rule we discussed earlier. Let's look at each prime individually. For the prime number 2, we have powers of 3, 2, and 3. The greatest among these is 2 cubed. For the prime number 3, we see powers of 1, 2, and 0. Remember, 3 to the power of 0 is just 1, so the greatest power here is 3 squared. Finally, for the prime number 5, the highest power present is 5 to the power of 1. Finally, step 4, calculate the product. We multiply these highest powers together. So, the LCM of 24, 36, and 40 is 2 cubed times 3 squared times 5 to the power of 1. When we calculate those values, we get 8 times 9 times 5, which equals 360. So, as you can see, whether you are dealing with 2 numbers or 3, the method remains identical. Just be careful not to miss any primes, as we will discuss in our next slide regarding common mistakes. Common mistakes to avoid. First, a very frequent error is confusing the LCM with the HCF, or highest common factor. When we were looking for the HCF in our earlier discussions, we were looking for the smallest power of only the common primes. However, for the LCM, you must remember the rule we just learned. HCF equals the smallest power of common primes, but LCM equals the greatest power of all primes involved. Don't let that distinction slip. Second, be careful not to ignore non-common primes. Sometimes, a prime number might appear in the factorization of one number, but not in the others. A common mistake is to leave that prime out of your final calculation. Remember, for the LCM, if a prime appears in any of the numbers, it must be included in your final product. We cannot leave any prime factor behind. Finally, please watch out for simple calculation errors involving exponents. It sounds basic, but in the heat of a complex problem, it is easy to miscalculate. For instance, ensure that 2 cubed is calculated as 8 and not 6. Always take the time to evaluate your powers fully before you move on to the final multiplication step. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the steps we've covered in the previous examples, it is very easy to make a few specific mistakes that can lead to the wrong answer. If you can avoid these 3 traps, you will find this method to be incredibly reliable. Key takeaways. First, let's revisit the definition. Remember, the least common multiple, or LCM, is simply the smallest positive integer that can be divided by all the numbers in your set without leaving any remainder. Next, I want you to memorize this core rule, as it is the heart of this method. When you are looking at your prime factors, you must always select the greatest power of every prime factor that appears in any of your numbers. This is the fundamental difference between finding the LCM and finding the HCF, which we touched on earlier. To keep your work organized, just follow this 4-step process we've practiced. Start with prime factorization, then list every prime number you see. Next, pick out the highest exponents for each of those primes, and finally, multiply them all together to get your result. Lastly, keep in mind the scope of this method. Whether you are dealing with just 2 numbers, like we did in our first example, or 3 or more numbers, like in our final example, this systematic approach will always work. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways to ensure you have a solid grasp of the prime factorization method for finding the LCM. As long as you avoid the common pitfalls we discussed, like forgetting non-common primes or confusing the powers, you will find this method to be incredibly reliable. Great job today!